Welcome back for part 3. The phone cut off again. I think maybe it's going to do better this time. But I also rewrote things on the screen so it would go better. Hopefully. And of course I'm wasting time drinking. All right. But I'm thinking, oh, I have to talk a lot. I need a little bit of water. Okay. So where we stopped was right here. And I was telling you that there's 4 ways of saying the same thing. And it's all saying that the nucleus that wants its electrons holds them in tight. And it takes a lot of energy to take it off. But the nucleus that doesn't want its electrons holds them loosely, and it's easy to grab one. So the first one is called electronegativity. And that is the ability to attract electrons to itself. The ability to hold them close. So I would write this, if I were you, on your periodic table, and I made it red. And as you go down a family, this ability decreases. The nucleus has more and more children. You can't hold them all close. Like, you know, when my kids were little, there was a dog across the street who would come over and try to bite them. I could grab pretty much all 3 of them up at once when they were little and run in the house with them. He was just a mean dog, and he would bite at their faces. So, but my sister, who had 6 kids, there's no way she could grab 6 kids at once, because they weren't all babies at the same time. She didn't have sextuplets, whatever you call 6 babies. She didn't have that. So that ability to hold electrons to itself, electronegativity, decreases as you go down family. But it increases across the periods. As it goes across the period, they want their electrons, they hold them tighter, and so its ability to attract electrons to itself is stronger. The next way of saying the same exact thing is ionization energy. Ionization energy is the energy it takes to remove an electron. How much energy does it take to steal that little electron? Well, as you go down a family, it decreases, and it's easier. The more kids you got, I remember one time I was with my sister and her 6 kids at Walmart, and we lost Philip. We lost her first boy, number 2 child. He was just gone. It was like, we really didn't think about anybody stealing him. And in a little while, we found him in the middle of the clothes. You know, you open him up, there he was, all crouched down. He was poking his head up every now and then like a groundhog coming out of the hole. So, you know, the more you have, the harder it is to keep up with them. So the energy it takes to remove one is less. So, and that energy decreases as you go down a family, and it increases as you go across a period. It's the same trend as the ionization energy, because it takes if you want your electrons, then it would take a lot of energy to pull one away. If you don't want it, it takes no energy to pull it away. The third one that's saying a lot the same thing is shielding effect. And shielding effect is that the power of the nucleus is blocked by electrons. So, and that was back up there where we had David. David was my sister's 4th child of 6. And I think he might have been the smartest. I don't know. But he never got in trouble. He always made sure that if he was going to do something bad, that there was a couple of siblings between him and Mom. So he never got punished. He was just too far away. She was just like, oh, whatever. It's fine. So that shielding effect happens in atoms too. The more electrons there are between the nucleus and the electrons, the less power that nucleus exerts on the electrons, and they spread out, that they get further and further away. So as you go down a family, this one flips, this is blue, it increases, shielding effect increases, but then as you go across, there is no change. I wrote no triangle because remember, triangle, the Greek letter delta, means change or difference in science and math. So there's no change as you go across the period. Because as you're going across, the atoms are holding their electrons closer, and that makes them where those electrons can feel the power of the nucleus more. So it cancels out. Even though there's getting to be more of them as you go across a period, it cancels out. The fourth one is element size. So, of course, as you go down a family, it gets bigger. You're adding more electrons, it gets bigger. But this is the weird one, so get it in your brain. As you go across a period, they hold their electrons in closer. And even though they've got more neutrons, more protons, more electrons, they actually get smaller because they pull those electrons in close. So the atomic size decreases as you go across a period, increases as you go down a column. Now, bonding. Ionic bonds transfer electrons. Covalent bonds share. Ionic bonds are the ones who put their electrons up for adoption. Covalent, divorced, they have a sharing arrangement. Now the overall compound must be neutral. So that's why we have 1 minus 1 is 0. We're going to be doing math in a lab activity. For some of you, you'll be doing it on Monday. Others of you did it on Thursday. So this is why. If you were out, you'll be able to make that up. But overall, the atom has to be neutral. So the math is easy, but you'll be doing problems like 1 minus 1 is 0. It'll be like first grade again, right? Now, so first we're going to talk about ionic bonds. What holds them together is the cation loses the electron, the anion gains the electron, the cation becomes positive, the anion becomes negative, and opposites attract. And how you can remember this is we have a very positive, sweet kitty cat here. So you can remember that cations are the metals and they're positive. Now, I know some of you want to disagree with me about cats being positive, but I think we'll all agree when we come to the anion. Our anion is a fire ant, and we hate fire ants. I had some trying to build a hill in my room here at school. That you just went under the door and started building a fire ant hill right by the door in my room. And that is very negative. I do not want to be bit by fire ants while I'm teaching chemistry. So anions are negative, and it's not antions. We just call them anions so we can remember. All right, so next, so opposites attract, that's our heart. Cations are positive, kitty cat. Anions are negative. Now here are some examples. What you do is you look at the periodic table, and if it's in the first column, it's going to become +1. So lithium is +1. Now, notice, I don't know if you can see it, but I don't have a 1, I just have a plus. Why? Because we want to be cool like math. You know how math has understood ones? Remember in algebra, you don't write 1x, you just write x, and it's understood to have a 1. You're all cool like that. Well, we want to be just as cool as mathematicians, we scientists. So we have our own understood ones, and this is one place we just put a plus. No 1. Yeah, we're cool like that. Magnesium is in the second column, and remember I told you to write a +2 on it, so it becomes +2. Aluminum is in this third column. We ignore the hippies. We pretend like they're not there. And the third column over is what aluminum's in, so it becomes +3. Fluorine is in this column right here that's 1 away from the noble gases this way, so it's -1, but once again, we don't write the 1. We got to be cool like math and not write the 1 and have it understood. And then sulfur is 2 away in this column, so we write -2 here, -3 here. Now this column in the middle, write skip on, because that one doesn't usually make ionic compounds. Usually they just make covalent. So there's a pattern. Hey, you want to be in my video for the kids who are out? Miss Olivier will come talk. All right, she knows this. There's a pattern. 1, 2, 3, skip, -3, -2, -1, zip. One day I forgot, and I think Miss Olivier was here, and I was going 1, 2, 3, skip, -3, -2, -1, dip. What is it? And all the kids went, no, it's zip.
It's zip. I could say hello.
There's Miss
Hello.
Olivier.
I guess it's across the hall.
All right, so Lewis structures help with this. Remember when we learned those? If you make those Lewis structures, you can see what it wants to lose, what it wants to gain. And it also helps us understand later in covalent, and we're going to do a lab with that. All right, so in class we had a little hands-on review break where we did Lewis structures, but you're not in class, so we're gonna go on. There are some rules. You always write the cation first and the anion second. So our classic little compound we think of here is sodium chloride. It is an ionic compound, table salt. And it's called sodium chloride, not chloride sodium. Always cation first, anion second. I'm making a video for the kids who aren't here.
Oh, you're in the middle of it. So sorry.
Now Mr. Myrick came by.
Pretzels and marshmallows for Monday? You want me to get them?
Yes, absolutely.
Okay.
Sounds good. All right, so come to class Monday, pretzels and marshmallows. All right, next, for what you do is you write down the symbols, or you can write it over the name. You figure out what charge they're gonna have. You can consult your periodic table you filled out now. Then you figure out, okay, does it equal 0? Sodium is +1, chloride is -1, 1 minus 1 is 0. Yay, it does. So I get to just write them together. NaCl, sodium chloride, no subscripts. Okay, so let's try another one. Calcium fluoride. Calcium is on the +2 column. Fluoride is on the -1 column. So I'm going to write +2 by the as an exponent, a superscript by calcium, and -1 by the fluoride as a superscript, as an exponent. Now, is 2 minus 1 0? No, it's not. So we're going to have to do something. And what we end up doing is we need to have 2 fluorides for every calcium. So calcium will give 1 electron away to 1 fluoride, and then fluorine, we'll call it, well, I haven't gotten to, it'll be fluoride, but right now you just know it as fluorine. It'll give it away to 1 fluorine, and it'll give another electron away to another fluorine. So this is like someone who adopts out their children, and one child goes to one family and one goes to another one. We know people like that, don't we? I bet everybody knows somebody like that. Okay, and so now then it's balanced, because then it would be 2 minus 2, and 2 minus 2 is 0. Yay. Now, there's a little trick. You can think of it all through logically like we just did, but actually, whatever the superscript, whatever the exponent is for one atom, it will end up being the subscript for the other atom and vice versa. You write them down without any plus or minus, and if it's a 1, you don't write it. It's understood. So the +2 from calcium becomes the subscript 2 with the fluorine, and the -1 with fluorine becomes the understood 1 with calcium, and the formula is CaF2. Now, so they just cross. So we got applesauce here, crisscross applesauce. You just drop them down, cross them, and take away the charges. So we have a worksheet with that. It's posted on Canvas, I think. Yeah, I know, because I'm pretty sure I took a picture of it. So we're going to start doing parts of it, only the ones with the dots by it. Okay, now this naming system follows rules that's made up by IUPAC, the International Union of Pure and Applied Chemistry. And part of the rules is if it's binary, meaning it's made out of just 2 elements, then you write the cation, then the anion, but you change the ending of the anion to "ide." And that's why it's not sodium chlorine, it's sodium chloride. On your toothpaste, you'll see stannous, not fluorine, stannous fluoride is what helps your teeth not have cavities. So here are some examples for the names. Aluminum, AlBr3, aluminum is aluminum. Bromine, you change to bromide, aluminum bromide. NaCl, sodium, name it first, and then it's not chlorine, it's chloride, sodium chloride. Now, there are things called polyatomic ions, and you're going to have a quiz on them. Yay! Yeah, they're on that sheet of elements you're supposed to have learned. If for regular chem and honors, I'm giving it out to you on Monday. Yeah, you got to learn it too, not just regular. But anyway, these are atoms that work together they bond covalently to each other. They're like the divorced parents. But then all together, acting as one, they will gain or lose electrons and become an ion. It's called poly, many, atomic, atoms, and there's a chart of them. So if it is a polyatomic, no longer binary, but a polyatomic ion involved, then you get the name off of the chart. That's easy, isn't it? So for example, sodium hydroxide is a very common chemical. It has a common name. If you ever hear a lye, like lye soap, not telling lies, but lye soap, that's in it, sodium hydroxide. So it's NaOH. I'll write it up here. Oh, we're not going to draw, we're going to erase. It's NaOH, and it's the sodium plus the polyatomic ion. See how we have two capital letters? That's how we know it's polyatomic. And its name is hydroxide. So sodium hydroxide. Now that is not table salt. Table salt is sodium chloride. You do not want to eat lye. That's the same thing that's in Drano. That'll kill you if it's straight up. Let's see. Let's scroll on. Okay. We talked about that. Okay. Now, there are some ancient metals. See why we have a Roman here? Ancient metals. They're the metals that are here in the middle part. I won't dress sure with my water. They're here in the middle part of the periodic table. They're the ones that have been around forever. Gold, silver, iron, tin, copper. And they're the ones whose names don't match their symbols a lot of times because they've been around so long they got Latin. Okay, so some ancient metals have more than one ion that can form. So, and how you know which one it is they'll have the cation, the metal, followed by a Roman numeral that will tell you the charge. That's supposed to be what we do. And I was told in the 80s, when I was your age, that we were going to this new system. But have they? No, they have not. Both systems you see equally. It's just like in the 70s when I was a kid, and they said we were going to the metric system, and did we? No, we just have both. We have liters of Coke and gallons of milk. It makes no sense because we end up going in the middle and having both. And my son, Nathan, is the doctorate chemistry program at Georgia Tech. And I asked him, because they're one of the top schools in the world for chemistry. I said, do they still use the Latin names? He said, yeah. So they're not going anywhere. It's just like gallon jugs and miles. They're not going anywhere. So anyway, this is how it works. So the Latin name for iron 3, the ion that makes +3, is ferric. The Latin name for iron 2, the one that makes the +2 ion, is ferrous. So you either, for the name, will either be like ferrous, and then the anion, or else it will be iron 3. This will make more sense when you do your homework worksheet. I'm going to pass out to you a chart that's got all the ancient ones on it. All the ones do that. Or I might have you write it on your periodic table so that you've got all your resources together. Okay, now when these ionic compound forms, they are arranged in crystal lattices. They make crystals. That's fun. And too bad that you're on video because I brought a crystal to show everybody, and I don't think it'll come all the way over here. I brought one of those salt lamps. Have y'all seen those? They're like pink, they got a light, they glow, they're a big old crystal. And that's an example of one. And we're going to do a lab where we are going to find out the characteristics